Now that we've covered the topic of descriptive research, let's talk about experimental research. Now, like I've said, experiments are what people typically think about when they think of conducting scientific research. And an experiment is specifically the manipulation of one or more variables under controlled conditions so that the resulting changes in another variable can be observed. So with experiments, we are specifically changing one factor of an environment that we're observing in order to see if that change in one will influence a change in another. So this is specifically allowing us to detect something we call cause and effect relationships, or a causal relationship, where we can say that if we change or manipulate variable A, and it leads to a change in variable B, then we can say that changing variable A causes or leads to a change in variable B. Now, this is different from our descriptive research, where we were just measuring and describing the different things that we were looking at. So with those descriptive measures, we could only make sort of associations. We could say that maybe these two things tend to be associated. But when we're actually doing the manipulations, when we're actually conducting an experiment, that's when we can infer causality. So here, we're going to be testing theories through controlled experiments. And experimental research is driven by hypotheses. So what is the difference between a theory and a hypothesis? So a hypothesis is a tentative explanation or prediction about some phenomenon. So a hypothesis is something specific. So we're going to say that if something is true, then changing A will lead to a change in B. A theory is a more broad statement, so it's a set of formal statements that explain how and why certain events or phenomena are related to one another. So a theory is why we think that things are related. So our theory might help inform what we predict will happen. It can inform our hypotheses, but the theory is going to be sort of broader and bigger, and then each experiment will test individual hypotheses that might be true if our overarching theory, if our overall idea of how things work together is correct. So what makes a good theory? We have a couple of different characteristics that make a theory a good one. We want our theory to be consistent with prior observations. Basically, the predictions that come from our theory should be supported by research. It should fit with what we already know about the topic in the literature. A good theory should conform to the law of parsimony, and the law of parsimony is also called Occam's razor. And this is basically the statement that, given everything else being equal, the simplest explanation is most likely the best. So that's a fancy way of saying that a good theory is as simple as possible. We always want to start with the most simple explanation, and if we need to, if our simple explanation is falsified, then we can look at more complicated explanations. But you always want to start simple and complicated if necessary, as opposed to going the other way around. A good theory should also be specific. We want to explain how things are related to each other, not just that they are related. A good theory should lead to measurable hypotheses. We want to look at predictions that we can measure. For theories, because we're specifically talking about experiments, a good theory would allow us to establish causality. So if we can measure it and be specific about what it is that we're looking at, if we have that sort of, if this theory is correct, then we should see these hypotheses, that helps us establish causality. There's a little bit of an asterisk there because you can have a theory even if it isn't testable through experimental means. So maybe for some reason, maybe it's not ethically possible to conduct an experiment. You might be stuck relying on correlations and other kinds of descriptive statistics rather than experimental methods. So it's not always possible to establish causality, but if at all possible, it's a good plan. And the last thing about a good theory is that a theory should be falsifiable. And it means that it's something that we can actually test, that there should be some kind of observation that we might be able to find that, if we saw it, would show that our theory was wrong. So we're specifically saying that it has to be something that we can quantify, that we can actually test. So you can't just say that my theory is that Cadbury is the best chocolate, because there isn't a way to actually test that. We can't falsify that by saying, well, this situation proves that's wrong. So we would want to say, set everything up in a way that we can test it. So maybe we would say, instead of it's the best overall, maybe we say that it's rated most highly among a particular population. That's something that we can actually test. But best overall is very difficult to quantify and very hard to falsify. So it's not a good theory. As we continue talking about experiments and setting up experimental studies, we're going to want to talk about a couple of terms, and specifically a couple of kinds of variables that are very important to understand when you're doing research. So we already mentioned that variables is any factor that can change or vary in an experiment. Our variables are the things that we're looking at. So we can have an independent variable, or an IV, and this is a variable that the experimenter manipulates. This is the thing that we want to change. This is the thing that we think is causing the relationship that we're testing. So our independent variable is the thing that we change ourselves, that we are manipulating in our experiment, and that should lead to a change in other things. But it's independent because we have to change it ourselves. Our dependent variable, in contrast, also called a DV, is the variable that is affected by the manipulation. So our dependent variable will change depending on our independent variable. So this dependent variable is the thing that we're trying to measure. So we're looking at how our dependent variable changes when our independent variable is manipulated. So we're asking, how does X, our independent variable, affect Y, our dependent variable? We also might want to consider things like extraneous variables, which are sometimes called confounding variables. And this just means that they are extra things that are going on. They are uncontrolled events that can actually affect the outcome of our research. So a confounding variable is anything that can influence our dependent variable, anything that can cause variation in our variables that isn't directly linked to our manipulation of the independent variable. So maybe you have a really inaccurate ruler. Maybe you can't see all of the numbers on it, but you're trying to measure lengths. And so you have to guess a little bit. That measurement error would be a confounding variable. The accuracy of your ruler is something else that's influencing what we measure, but it isn't specifically related to the independent variable that we're manipulating. So these extraneous variables or confounding variables can pop up from all sorts of different sources, so we want to be aware of what else might be going on that could be affecting the system that we're looking at, because these can cause lots and lots of problems when you do research. Some other important things to consider is who you're doing research on. So we might want to differentiate between a population and a sample. So a population is the entire set of individuals that you want to draw a conclusion about. So if you want to know about how humankind's brains work, you want to know something about memory, the population is all humans. Our sample is a subset of the individuals that we draw from the population. The sample are the people that we are going to conduct our experiment or do our research with. They're going to come from our population, and if we've done our jobs correctly, a sample should represent our population. So if we're trying to study brains, then we want a sample that represents the brains of humans across the whole world. So we can have different kinds of biases in our samples, but we'll come back to that in just a minute. First, I want to talk about how we actually obtain a sample. So how do we choose who we're going to study from our population as a whole? So the first of these is a simple random sample. This is a setup where everyone has an equal chance of being chosen. So this could be something like, we have a class of, say, 300, and I need 30 people to help with a particular study. So I would put everybody's ID number into a random number generator, and I would select 30 completely at random. So everyone has an equal chance of being selected. So that is a simple random sample. Our next type of sampling is called stratified random sampling. And this is basically when you divide your population into subgroups and then take representative samples from each of those subgroups. So maybe in the class, we don't have an equal ratio of males to females. So maybe I would, there's a 70 to 30 split. I'm not quite sure what the ratio is, but let's say it's 70 to 30 males to females. And so we want our random sample to match the distribution of our population. We want a representative sample. And so we would take out of, say, the 30 individuals that I would like to study, we can randomly sample 70% of them from the male population and 30% from female, or whatever. And you can use these for different groups, different divisions, whatever's relevant to your research. So it might be that you want to take a certain number of people who are a specific age, or who come from a particular background, or who speak a specific language. So you are sort of intentionally stratifying or dividing up your population into groups so that your sample is more representative. This is really helpful if you have say small groups, so groups that only have a couple of individuals. With random sampling, it's very easy to miss very small portions of a population. So this stratified random sampling ensures that you have a more representative sample if you have a lot of small groups that tend to be missed with random sampling. The third type is non-random sampling. So this is basically saying that due to some kind of study constraint, not everyone has equal chances of being selected. And if you get into a methods course, you can break down different kinds of non-random sampling. Sometimes you start with, say, a convenient location and ask people to recommend their friends or others that they know that fit your criteria or something like that. But basically, non-random sampling is basically when we cannot random sample for some reason outside of our control. And the last kind of sample is a convenience sample. And this is what tends to happen probably more often than it should. And this is what happens when you work with what you've got. So for example, research participation works with undergraduate students at university because that's who we have access to. So it is a convenience sample that doesn't necessarily represent the population as a whole, but it's the best we have available to us. So we will use that sample even though it isn't representative of the population as a whole. So you have to consider the fact that it's a non-representative sample so that your conclusions, maybe you don't try and make very broad conclusions because your sample wasn't representative of the whole population or something like that. And so we've used this term a couple of times, but have a real definition for it. A representative sample is basically just a sample that reflects the important characteristics of the population. So these characteristics can be any factor that's relevant to the study that you're conducting. So, like I said, it could be age or background or language spoken or anything that is important to your study. And so random sampling should be a way where we can get a representative sample, minus some of the exceptions that I described. And for those who prefer visuals, we have a representative sample where this is our population overall. So maybe this is all humans. And they have these different categories that they fall under, A through H. And we have some kind of sampling procedure. Maybe it's random, maybe it's convenience sampling. If we have some kind of random sampling, we should end up with a representative sample. And you'll notice that the proportions of these different groups is fairly similar, if not identical, to that of the original population. Our sample does a good job representing the population as a whole. If we use some non-random method, we'll usually end up with what's called an unrepresentative sample. And for some reason, these groups aren't distributed the same way in our sample as they were in the population. So that might not be the best thing to use. But as I've mentioned, it's not always possible to randomly sample. Sometimes you just have to design your research with the idea that you can't randomly sample in mind. Sometimes you take into consideration the limitations of how you can generalize your results, and sometimes you just realize that you might have to conduct follow-up studies to see if this holds true across multiple groups. Using a non-random sample can be okay in a couple of specific situations. The first of these is that you can get away with a non-random sample if the similarity of a sample and a population doesn't matter. So what this basically means is if you're trying to do something like, maybe you want to look at the structure of the brain overall. Maybe you don't care about small changes or small details or different activity levels or anything. You just want to study the anatomy of the brain. Then maybe it doesn't matter how old someone is, or maybe it doesn't matter if they're from Canada or the US. So you might not need a random sampling of all humans to look at the anatomy of the brain, because all brains are going to be more or less the same as far as your research is concerned. It might also be okay to use a non-random sample if you're going to be using multiple experiments conducted on different samples, and if those different experiments on different samples all have similar results. So maybe you do a study and you're limited to the research pool at the University of Alberta. So you're stuck with Canadian undergrad students. But you want to see if the results hold true for, say, people in Japan. So maybe you partner with a university that does research in Japan. And so they find the same results, but this time in undergraduate students in Japan. So that gives you some idea that, okay, it's not just Canadian students, it's also students in Japan. All right, what about we also look at say, people from Australia who are in a nursing home. So a different age group, a different location again, and we find the same results again. Because we're seeing the same results or similar results in different samples, in different areas, in different ages, in different groups, that gives us some more confidence that even though each individual study doesn't have a representative sample, the fact that we're seeing similar results across multiple studies, that makes us more confident that what we're seeing is actually generalizable and that we can apply it to other situations. And sometimes we can get away with having if the similarity of a sample and the population is reasonable. So sometimes you can get it close enough or as close as it matters for your specific study topic, and that is going to be okay. Again, you will occasionally, or pretty much always, keep in mind the limitations of your design, especially when trying to draw conclusions at the end, but there are situations where you can get away with using a non-random sample, and sometimes you have to. All right, so we've talked about how we get our samples from our population. Now what are we going to do with them? And so what we typically do in an experiment is that you'll break people into two groups. you will have an experimental group and a control group. So, an experimental group are subjects who receive some kind of special treatment in regard to the independent variable that you're trying to manipulate. So, maybe you want to see if studying more leads to improved grades. So, maybe you have an experimental group where you get them to study a lot, and then you have a control group, which are going to be made up of similar subjects, but they don't receive the special treatment, the thing that you're trying to manipulate. So instead of getting extra study time, maybe they don't study. So we're comparing our experimental group to our control group. And sometimes you'll actually see the control group called a comparison group, because they're not always sort of a null group. They're not always no treatment. Sometimes there's some other kind of comparison. But we'll talk about some of our special cases in just a minute here. So typically what we see is an experimental group where they receive some kind of manipulation, and a control group where things are held constant. And the logic here is that the two groups should be alike in as many aspects as you can. So we try and make these two groups as similar to one another as possible using a process called random assignment. Now, don't mix up random assignment with the process of random selection. Random selection is when we were picking our sample from the population. But random assignment is how we take the people that we selected for our sample. So we have our sample, the people who will participate in our study, and we're going to randomly assign them to be either in the control group or in the experimental group. So by splitting them up at random into those two groups, hopefully the two groups should be similar in composition. So we can check that by measuring things like age and sex and whatever else is relevant, just to make sure that there aren't any other extraneous variables going on in the background. But random assignment should ensure that our two groups are effectively identical for the purposes of the experiment. By manipulating that independent variable in only one group, in only the experimental group, we're then seeing how changing that independent variable by manipulating that one factor can lead to a change in the thing we're measuring. Because we haven't changed anything in the control group, then any difference between the two groups should logically have been due to that manipulation of the independent variable. So if the only thing different between our experimental group and our control group was that the experimental group was given extra study practice, and this experimental group did better or performed better on their test, they had a higher score for their dependent variable, then we would conclude that studying more led to an increase in their test scores. Now, I did hint at the fact that there can be extra variables that are involved, those confounding variables that go on in the background. Sometimes the act of actually manipulating your independent variable can introduce a confounding variable. So if you think of something like administering a drug, maybe we're looking at a drug trial, and so our experimental group will be receiving a drug that's supposed to help reduce anxiety. The control group doesn't receive that drug. If the control group doesn't receive anything, then they know that they're in the control group, and so they might not realize that, let me start again. The control group, by not receiving anything, knows they're in the control group, and their behavior may change depending on that. On the other side of things, the experimental group got that drug, and therefore they know they're in the experimental group. And this actually can lead to the placebo effect, which is basically where the effect of a treatment comes out of actually a parent's expectations, but not from our manipulation. So the patient in the experimental group received the drug, but they do better not because of the drug, but because they think that they should improve. So our minds are really good at influencing our behavior, even subconsciously. So, what we can do to get around this, what we can do to control for that confounding variable of this placebo effect, is that we'll actually use a placebo. So, what we'll do is our experimental group will receive, say, the drug in a capsule, and then the control group will receive a capsule that's maybe filled with something inactive, something that doesn't affect them at all. So both groups receive a pill, and both groups assume it will help, but only one group is actually receiving the drug. This can be used in a lot of different ways. Maybe you have, so for injections, you would have an injection of a drug and then an injection of saline to match both groups on that factor. Or maybe you have one group read an article that educates them on a particular topic, and then the other group reads an article that isn't related to the activity at all. So they both read something, but the content is different. There are lots of different ways that you can employ placebos in experiments to ensure that your control group and your experimental group only differ because of the effects of manipulating that variable and not on the fact that there was a manipulation or not. Now, this experimental group, control group, is sort of the standard setup for a generic experiment. But I have hinted at the fact that there are lots and lots of different variations that you can take from this basic setup. So I'm going to cover a couple of different variations that we might encounter as we work through this course. So the first of these is to expose a single group to two different conditions. So rather than having an experimental group and a control group and having them be made up of two different sets of individuals, maybe we would have the same group experience both the manipulation and be their own control. This would be a fantastic way to help control extra variables, our confounding variables or extraneous variables, the other stuff that might be going on, because everything is held constant in the background. And I actually have a separate slide right here, which helps illustrate this difference. So the standard type of experiment that we talked about at the very beginning is a between groups or between subjects design. And this is where each group in the experiment is composed of a different set of participants. So for a visual representation, we have group 1, and they receive treatment 1. So that's the experimental group, maybe. In group 2, they would receive the second treatment. Maybe that's the control group. They receive the placebo. But this group and this group are separate individuals, so we're looking at the differences between two groups or between sets of subjects. The other option, where we're having exposure, the single group exposed to two different conditions, that's called a repeated measures or within subjects design. And this is because each participant is going to be exposed to all of the conditions of our independent variable. So back to our visual here, we only have one group of participants this time, and they'll be exposed to treatment 1, which might be our experimental treatment, and then after that, they'd be exposed to treatment 2, which might be our placebo. And when you're doing this, you would typically do it so that some receive the experimental manipulation first, and then they would experience the placebo. And then in some other people, they'd get the placebo first and then the experimental treatment, just again to control for all of the extra variables that might happen. But this is one method of changing things up. So you can use a repeated measures design instead of just a between groups design. You might also manipulate more than one independent variable. So you might start looking at things like interactions between variables. And I do have another slide for this one here. So maybe we wanted to look at multiple things. So we wanted to look at performance in driving. So our dependent variable is how quickly people can brake in reaction to something coming up in front of their vehicle. We might want to look at our first independent variable, which is whether they're on their cell phone or not. So if they're driving with no cell phone or driving With a cell phone, that's the first variable that we're looking at. If we want to introduce a second independent variable, maybe we want to look at something like traffic density. How busy is it? Is it not very busy, or is it very busy? So we can ask then, looking at, okay, so what if somebody is driving no cell phone in low traffic density? They're going to be able to brake fairly quickly. If they're driving with no cell phone and the traffic density is high, we'll still see that they're doing fairly well. They brake about the same amount. So the traffic density doesn't matter if they're not using their cell phone. But when we look at the interaction here, when they have their cell phone and there aren't too many cars on the street, they stop a little. It takes a little bit longer to stop, but it's comparable. They're doing an okay job. But when we see cell phone use and high density in the traffic, then we see it takes a lot longer to brake. So there's more going on, they're more distracted, and we see here an interaction between multiple independent variables. And so this is an example with 2. You can get into far more complicated statistics, look at 3, 4, or more independent variables. So you can start breaking things down in a lot more detail. And that lets us study those interactions. You can also, as you might guess, use more than one dependent variable. So instead of just measuring braking time, maybe you wanted to look at number of times they scan the road, or speed, or whatever you want to measure. So if you can measure multiple things that might be affected by your manipulation, that gives you a more complete picture of the effect of that manipulation to your independent variable. So we get a better idea of what's happening, of what's being influenced by that manipulation. So these are just a couple of the ways that you can get away from our standard basic experimental design. And so, of course, we want to talk about what are the advantages and disadvantages of conducting experimental research. The biggest advantage that we've talked about already is the fact that experiments allow us to make conclusions about cause and effect. So if we conduct an experiment, we can make conclusions about causal relationships. So this gives us a lot of power to figure out what's driving different scenarios because of those manipulations. We do, however, have some limitations to consider. So with experiments, a lot of these are going to be conducted in a controlled environment, which can be good because it's helping us control those extra variables, but it can lead to sort of this artificial environment. So it might be hard to sort of generalize our conclusions from an experiment conducted in the lab to maybe something that's useful that we could apply in the real world. So we need to keep in mind that experiments are fairly artificial in nature because we're controlling for so many other factors. But if we want to be able to make those causal conclusions, then we need to control for all those other factors. So it's a fine line to balance there. We also need to keep in mind things like ethical and practical concerns. There are definitely certain things that people might be curious about, but it's not ethical to study. So you can't do manipulations that would say, I don't know, cause harm or make people uncomfortable or whatever bad thing. Basically, you can look at a bunch of early psychological experiments and question the ethics of having conducted some of those. So for ethical reasons, certain types of experiments just can't be done. So if that's the case, then you're stuck with correlational research. You're stuck with describing and measuring things as they are, but you can't manipulate them. And because of that limitation, then we can't make direct definite conclusions about causality, but we can give it our best guess. There are also practical issues where sometimes it's impossible to assign people to a particular condition. Sometimes it's only possible to measure things. We just can't determine if you do or don't speak a language. We can only measure that factor. So sometimes we're stuck with correlational methods because you physically can't set it up in an experimental way. So these are some things to keep in mind. And the last thing that I want to consider about our experiments is our experimental results, which will actually transition us over into statistics. But when we're asking if we trust our experimental results, we want to consider two major things. And these are both types of validity. So internal validity is the degree to which the results can be attributed to the independent variable and not other explanations. So basically, if an experiment has high internal validity, then we are very sure that the change in our dependent variable was caused by our manipulation of the independent variable. However, if an experiment has low internal validity, then there might have been other things, say confounding variables, that might be responsible for the changes in our dependent variable. So low internal validity means that we're not actually sure that we saw a causal relationship between our independent and dependent variable. So internal validity, we can have low internal validity if we have lots of confounding or extraneous variables. We can also look at external validity, and external validity is looking outside of that experiment. So external validity refers to the degree to which results can be generalized or applied to other people or across settings and across time. So if we conduct a study and we have a representative sample, then we might say that we have good external validity because our sample is representative of the population as a whole. So we can call that a strong external validity to our experiment. And we might be comfortable saying that our results that we found in this sample could apply to the whole population. However, if you had a very non-randomized sample or an unrepresentative sample, maybe we used a convenience sample and we're only looking at undergraduate students at a single university, that would be low external validity because we can't necessarily generalize to other populations without conducting additional experiments, kind of like we already talked about. So those are two types of validity that we need to think about when we're evaluating the results that we obtain from a study and whether we can make conclusions and apply them to sort of larger areas. So this is how we determine what do these results mean and what can we do with them.